Good morning, packed house. Thank you very much for coming to my talk. We'll be talking about building evolutionary architectures, and this morning's keynote is a really good sort of pathway lead into this. The sense of biology, metaphor, and evolution is really key to this idea about building evolutionary architectures. And I hope that you go away thinking a little bit about what it means for you to be evolving your systems and how you do this effectively. I work for a company called N26. We're a German bank based in Berlin. We like to call ourselves the first bank you'll love. And we really have a big focus on sort of design aesthetics, really trying to bring mobile banking to a user experience. Most recent sort of product is really trying to make Spaces an easy thing for you to manage money. And we're very proud of sort of the product that we've been building. We have more than 1.5 million customers in Europe. We are in the Eurozone, so not here in Sweden officially, but I am the CTO at N26. And what that means is I'm also responsible for helping us evolve our systems and architectures. I worked for 14 years at ThoughtWorks before that, and was helping a lot of other companies work out how do they start to evolve the systems that they've had over time. The contents of this is actually from my latest book, which I wrote with the ThoughtWorks CTO, Rebecca Parsons, and Neil Ford, who's been a frequent speaker here at Øredev as well, where you can find out more, and there's actually an O'Reilly course on this as well. But today we're really here to talk about evolution, and one of the reasons that we thought we'd use the metaphor of evolution in software is that you'll have noticed that the pace of change in software has really upped its game over the last kind of decade. So I've been working in software for about sort of 17 years. If you have also been working in software for so long, you probably start to understand the pace of change of software now is really different from what it was in sort of the 1990s or the early 2000s. And one of the things that you start to realize is, well, you know, this change thing is kind of unavoidable, whether or not we want it, whether or not it's something that we appreciate or not, it's going to be inevitable. And this is kind of the realization that I've come to over time, really starting to understand that we have to build our systems for change. And when I think about the types of changes that I've had to build sort of systems for, you can kind of think about them in sort of two different domains. And so a lot of the content here, perhaps at this conference, will be really thinking about one side of that change, which is the technical side, right? So these are all the things that we as engineers are very much used to. We're very much used to all the changes in programming languages, the libraries, the frameworks, tools, operating environments, and technical constraints. So cast your mind back sort of 10, 15 years ago, most of you may not have had a sort of smartphone of some sort that were just starting to come out. Today we have very good bandwidth on our sort of smartphones as well, which allow us to sort of access applications in a very different format from what we used to have. When I started working, it was all very much about desktop applications that you would install, have to constantly think about updating, and it was a very different market. And then the internet came along, we started thinking about web applications, and today it's very much about mobile, web, and desktop. So it's a very complex ecosystem today. For many of you, you're also probably building cloud-based software as well, and that's also a huge different constraint about you no longer have to think about hardware provisioning. You never have to think about too much about sort of hardware racks and mounts. Some of you may, but you know, working in the cloud is very fundamentally different. And so we have to think about the practices that evolve in association with the ecosystem in how that's changing. But the technical environment's not the only things we need to think about in terms of change. We also need to think about the domain, and both of these co-evolve as well over time. So many of you are probably members of Spotify or Netflix, so some subscription service. And actually, it's very rare that we sort of buy something. We are now sort of opting more for subscription-based services. And this changes the way that we have to build software, because we have to think about how do we price? How do we account for every song that you listen to that some artist or producing company gets paid for as well? So there are inherent changes in the domain that we also have to think about in our sort of software to keep up to date. You can also think about in terms of new markets. So crypto is probably the latest one in sort of technology. Yet to see if it's going to sort of succeed long term, but it's definitely a big market out there with lots of companies competing to sell and build sort of crypto. And of course, every new market also produces new companies and products that you have to keep up to date. So lots of change, both technical and domain. And so we had this kind of premise of really thinking, if change is really inevitable, then what would that actually mean? what would we do differently? And so the premise of the book is really, what if we architected a system for change? And what would that look like in today's world? Now, some of you might be thinking, oh, this is going to be lots of big design up front. There's a lot of thinking about that. But that's not what we're really talking about. We're really talking about a system that is suited for its purpose and really thinking about how to keep it up to date as the ecosystem around it evolves and as the product itself evolves over time as well. So in exploring this question, we came up with a definition of what we defined as evolutionary architectures. And so we believe an evolutionary architecture supports incremental, guided change as a first principle among multiple dimensions. And in today's talk, I want to sort of explore the three elements that we believe make up a really good evolutionary architecture and give you ideas about how you can go about making sure that your systems evolve as well. So one of the sort of first concepts that we believe is really key to this is really this thing about incremental. And we believe that architectures are evolved through incremental releases. And this is where the idea of generations come back. So if you've studied biology, and I don't claim to be an expert of any kind, but one of the things that you learn in biology is really about generations and reproduction. And so for us in software, we believe that incremental releases are representing this generational concept. So if you think about a system that you might start off with of some sort, you might start to then think, well, what happens if we change it? What happens if we want to make an adaptation for this market? What happens if we experiment with this particular tool? Now, like biology, it's very hard to predict where these things might end up, but we may end up with 4 variants of some sort. And once again, over time, we may end up with very different systems that we couldn't actually have predicted, but we need to experiment. Now, the question you should ask yourself is, if generations are this incremental concept, how long does it take you to actually make an increment to your system? Is it in the scale of 6 months, 3 months, 1 month, or a day? And so this is where the biology metaphor of being able to evolve really rapidly is really key. If you think about generations, in software, we believe that generations equal the cycle time. And cycle time in software is this idea of taking a change all the way from when you make it all the way into production. And the key to this is really being able to do this repeatably and reliably. So this isn't a new concept, hopefully, for many of you. What we're saying and what we're positing is that in order to have a very strong evolutionary architecture, you need a basis of your software to adhere to the ideas behind continuous delivery. So if you can't get changes out into production, you have no idea if it's actually fit for the environment, and you're only guessing. And so the more rapidly you can get your software into production, the quicker you can roll it back if it's not fit for purpose, or the quicker you can make change. So this is where your leverage point is if you really want to evolve your software systems. Now, those of you who've been working with continuous delivery for a long time will know continuous delivery only touches one part of it. You also need the organizational culture around that as well. And this is actually where the DevOps kind of movement actually has emerged over time and is a strong complement to continuous delivery for it to be effective. So a really good book around this is the Phoenix Project, which I highly recommend if you've never read it. And if you want some concrete practices, the DevOps Handbook is also just as appropriate. Now, it takes not just the people to build stuff, but the organization processes and the practices to get continuous delivery right. But these are really the basis of fundamentals if you want to have an evolutionary architecture. Now, if you look at all of these movements, practices, and sort of cultures, there's a couple of key practices that we believe make a big difference. So the basis is definitely about continuous integration. The idea about automating everything. So as soon as you involve humans, you make mistakes, things don't become repeatable, they don't scale. And this is where you need the speed and you get the quality if you can make everything automated. Keeping everything under source control is a really great philosophy of being able to repeat everything and being able to restore that. Anything handcrafted will often mean that you'll end up with snowflakes and you can't reproduce that. Done means released into production. So it's not enough just to do Scrum of saying a potentially releasable artifact, but actually making a change and getting it into production, into the hands of users, getting it really production tested, and working out if the system is fit for purpose. And sharing release responsibility is a really key element of this as well, as is continuous improvement. Now, kind of go back to talking about architecture, and often we kind of think about architecture as a linear process. We start to think about, we have this business problem, we need to architect something for it, so we have this kind of architecture phase, and then we sort of write the code that meets that architecture, and then we release it. Before we go down this path, we probably don't have a shared understanding about what architecture is. Now, I've been working in the industry for a long time, and there isn't really a shared collective definition of this. So what I can do is talk about standing on the shoulders of giants, what other people describe as architecture. So let's explore this question. What is architecture? So Martin Fowler, chief scientist at ThoughtWorks, talks about software architecture as the decisions which are both important and hard to change. Now, that's quite interesting, because if it's hard to change and you make it easy to change, it no longer becomes an architecturally significant decision. It's just a design decision that you can revert. So what makes it hard or easy to change depends on your environment. Simon Brown talks about architecture is about understanding what you need to build, creating a vision for building it, and then making appropriate design decisions for that. Ralph Johnson talks about architecture, the decisions that you wish you could get right early in a project. I'm sure many have been there as well. Foresight, or hindsight is much easier. And so these are some of the interesting things, is that when we think about architecture as this linear process, we often start to think about architecting is where we make the important decisions over here, where we start to think about, well, developing is the easy stuff over here, and then releasing is, well, how hard is that really? Now, hopefully all of you realize that's not really how the real world works, and actually what we realize is what appears to be important when we architect are actually the things that aren't, potentially. When we actually write code and develop stuff, we learn a lot more about the problem space, so we explore that, and the environment might evolve as well, and we discover false assumptions. And then we know that releasing software is actually much harder than we thought. It's always a battle to make sure we don't break things while we're actually changing them as well. And so when you actually start to think about this architecture process, I really encourage you to sort of move away from this linear thought process to start thinking about it as a cycle of architecting, developing, releasing, and more importantly, also reflecting on whether or not you're making the right architectural choices. So architecture isn't a once-off process that you do at the beginning of a project and that's done. It's really thinking about doing it in phases. And once again, how you can actually test this is really about how quick you can get this through your cycle. And so you really want to be thinking about what you can do to reduce this loop and really reflecting on, are you making the right architecturally significant choices? And that will change over time. And so in software architecture, your cycle time is really your constraint to be able to test whether you make the right architectural decisions. Perhaps you made an assumption about scalability, and then you find out actually you need to be aiming for 5 times that. You don't really know that until you put it into production. You discover new things, and really you need to be thinking about putting things in the hands of users into the real environment to discover what is actually hard to change and what is architecturally significant and important. So that's kind of the first part of building evolutionary architectures. You need to have good continuous delivery practices, tools, and processes, and a DevOps culture for it to be successful. The second element that I want to explore about building evolutionary architectures is really this idea about fitness functions. And what we describe is that evolutionary systems are guided with fitness functions. So we take this from sort of the idea of sort of machine learning as well. So when you're actually doing sort of machine learning, you have an idea about what good looks like, but you're not necessarily telling the algorithm how to get there. And that's very similar here. In software, what we talk about is an objective function, so something that you can sort of say yes or no, that measures how close a given solution fits to a particular goal. And that's really key when you're actually thinking about systems. What is important for the system that you're optimizing for? How many people in your team know what is important and what they should be optimizing for? And so what we encourage people to do if you're going down this route is really going back to the ideas of these ideas about what are important characteristics that your system should be optimized for and make them explicit. So do a brainstorm with your business users, with your technical stakeholders, around what you think is important characteristics for the system. You might have called these non-functional requirements, cross-functional requirements, or system quality attributes. But it's really key to take them, identify them, and then classify them as to what system is important. Now, naturally, there'll be different types of systems even within the same sort of company. So you may have systems that are more for back office people, where there are different types of characteristics than your sort of public web application or your sort of main consumer sort of application. But what's really key is not necessarily simply identifying what's important. It's also bringing it back to something that's objective, so something that people can easily test, yes or no, the system is fit or not fit for this. Too many times I've seen applications sort of think about what is important, and then they get written down, and then they get forgotten about. So everyone's busy writing code, and then we release, we're really happy. But we don't really bring that feedback loop back in to test, did we actually meet the objective of the system that we're optimizing for? And has that changed over time? And so we encourage you to think about these objective functions through 3 different mechanisms. One through sort of metrics, another one through tests, and another one through the process of validating how you build your sort of software. Now, we've identified a number of categories of fitness functions, and I want to walk you through some examples of that. So I'll talk about what is an atomic fitness function, we'll talk about a holistic fitness function, and then we'll talk about continuous. And what's really key is that you can actually combine these fitness functions together, but it's really key to think about, depending on what you're trying to optimize for, having something objective that you can test a system for as it evolves. So the most simplest example of an atomic fitness function is wrapped up in this sort of JUnit test here, which is running JDepend. So if you want to prevent circular dependencies in your code base, you can write a simple thing like this and add it to your code base to avoid circular references. And we know that circular references make change really hard over time. And this is actually something you can put into your build process really easily to sort of make sure that you don't have circular references. Now, if you go one step further, you can actually tailor this even further and actually start to talk about what are strict layers which should call one layer on the other. So in this example, we have the web depending on the utility, we have a repository depending on the utility, web depending on the repository, and then any other sort of circular or any other invalid references across packages would fail the unit test. So you're giving this objective fitness function to all people as part of the code base, which means it can never be forgotten about, and people get really fast feedback. And that's the point. You're always going to be optimizing and validating your system is fit for the function that you build. So there's lots of examples of this that you can sort of think about. What are the things you put in place, like check style, to put patterns in to enforce the sort of architectural consistency that you care about. So an atomic fitness function is testing one element of your architecture. I want to talk about a holistic sort of fitness function, and it kind of needs a little bit of context. So there was a project that I was working on. We were brought in to help build, which had to do with a performance tuning problem. So this company had sort of a voice-to-text system. They received lots of voicemails, and they had a problem storing these sort of voice messages for a text conversion process. So they needed the system to scale. And so one of the key characteristics of the replacement system that we're building was really identifying that performance was particularly critical. And so what we ended up doing is we ended up building a CD pipeline of performance tests. So when we were starting to think about the new application, we needed to prove that it was going to work through lots of different examples. So like a high escalating load where load is continually increasing, perhaps a constant throughput over time to make sure that it always performed without any memory leaks. Something with a sort of sharp spike as well to make sure that the system was going to be optimized for this. And because performance was the most important characteristic of this, we decided it was worth the investment to automate the performance tests. Now, if you've done performance testing, you'll know that actually it can take a long time to actually get feedback from a performance test. So we also wrote a sort of sanity performance test, which would sort of do a small run to make sure that all the test fixtures work, and then would run a series of parallel to performance tests on different environments. So as I said, we had a memory soak test, and then one weekend, we came in and we found our build was broken. We're like, what happened? There was some unusual behavior detected in a test run. So in our sort of graphs, and I highly recommend you graph things when you do performance testing, we expected a constant throughput and sort of performance. But what we would have is every hour we would have a spike in latency in our sort of performance test charts. We're like, this is really odd. We don't really understand what's gone wrong. We haven't changed anything significant. So we sort of rolled back code to about a week ago, and then we ran the performance test again in the same environment. No, it all was working okay, and we still got this sort of spike. So we went back 2 weeks, 3 weeks, same sort of thing, same pattern of behavior. It's like, it can't be in the application code. We talked around to some of our operations people who were sort of running the environments. And after some investigation, we found out there were some changes in some of the environments. And where that spike was actually happening in our performance tests was actually a misconfigured disk controller. And so what happened was that there was a sort of storage SAN, and it would flip over every hour from one SAN to the other. And as a result, our application would actually have this sort of spike in latency as it was sort of switching over. And without actually testing our system holistically, we wouldn't have actually caught this performance problem. And this is really key when you start to think about not just atomic fitness functions, but you need something that tests the system as a whole. And I always encourage people to start to think about software more than just the code that they write, more than the application that they have. In today's world of distributed computing, we need to think about the ecosystem, the networks, the machines, everything that runs those sort of systems. And we need something that tests our systems working as a whole. And so that's a really good example of how you might think about testing a holistic characteristic of your software system. The third example of a fitness function is really a continuous fitness function. And the real prime examples of this is Netflix and their Chaos Simian Army. So if you're not aware of the Simian Army, Netflix have built a whole bunch of chaos testing tools, and they run them continuously in production. So they turn off network configurations, they slow network traffic down, they try to break systems and try to sort of reboot services. And what that has built over time for Netflix is really a robust system where the unpredictable nature of a distributed system, they've built in resilience. Now, at some point, they decided it was so important that they would invest in building the Simian Army, and they run it continuously in production. Now, there's a whole field of chaos engineering that you too can start to explore. You don't need to run these tools in production. You can also do chaos game days of trying to break your system in funny ways. But the idea, very similar to biology, is when you sort of get attacked, when you have a disease, your immune system gets stronger. And that's very similar with this idea of chaos engineering. You're constantly breaking the system, and the system gets stronger as a result, as long as you're working out how to fix it. Now, the really good example of where this paid off for Netflix is, if you remember, I think it was a year or 2 years ago, Amazon S3 went down. A lot of companies suffered. Even Amazon themselves, when you went to their website, went to Amazon.com, looked for something, there would be some images missing because S3 was down. Netflix was the only company unaffected by this outage. And this is because they invested continuously in this idea of a fitness function, which for them was important. I'm not saying you have to do it, but if it's important, you need to think about what you do to objectify and then put this as a fitness function in your environment. So what I really like about continuous delivery is this idea of if it hurts, do it more often. Not because we're sadistic, not because we like pain, but the idea is that we should get better. We should learn a lot faster. If we put things off, we're only going to delay the pain and we're not going to learn. We'll accept that pain once a year, but if we do it all the time, hopefully our systems get better, and our systems get better and meet the fit for function for what we care about. So there's an old saying that there are known knowns, and these are the things that we can objectify as fitness functions. There are sort of known unknowns as well, so we can extrapolate the things that we believe that we know about. But there will also be unknown unknowns. So if you can't read it here, it says psychic fair cancelled due to unforeseen circumstances. And one of the points of this is not trying to predict exactly where our industry is going, not to over-abstract where things are coming up. We don't know what things will pay off in our industry, but being aware that we have to be aware our industry will change over time, and we need to think about what things may be relevant for us as well. So not trying to over-abstract. And a really good example of this is, we used to have a lot of in-house data centers. Some of you may still have in-house data centers. There's now sort of a move to sort of cloud computing. And this is where we start to talk a lot more than cloud, but we start to talk about serverless as well, so platform as a service. And we're now also starting to think about sort of functions as a service, but who knows what will be next? We have to be thinking about where the next generation will lead us to make sure we're building our systems with the right basis as well. So we've explored the idea of incremental, we've explored the ideas of guided. What do I mean by multiple dimensions? This comes back to thinking about the types of dimensions of change and then asking yourselves, how does your software cope with those types of changes? And so there are the technical changes that we're sort of familiar with. These are changes that happen with libraries, tools, frameworks, and platforms. So we need to swap them out. We need to upgrade them. We have to configure them. Perhaps we have to remove security vulnerable software. And then there are also the domain changes. So the things that we have to do to keep our businesses competitive or our products competitive. Maybe about pricing. Maybe it's about features. And so really we want to be thinking about, in our software architectures that we build, how do we support both of these changes at the same sort of time? Now, it's best done through some examples. So we'll have a look at a few different types of examples. So we'll look at the big ball of mud, the layered architecture, kernel architecture, and microservices as a result. So this is actually from a project of ours. And this was a visualization of one call out from one class to another. Oops. And so if you have the sort of circles, you'll notice that there's a lot of lines throughout everything calling all over. In a well-modularized system, you'll actually find clusters in sort of parts of the circle. And so this is a very highly coupled, complex code base. And this makes changing a technical library really difficult, because you start to unweave something, you start to pull the other threads. There's no sort of cohesion in there, and there's not a lot of decoupling. Now, if you have to make a pricing change rule, you have to scan the entire code base to think about where you might actually make that pricing change. And so the big ball of mud, hopefully you don't have to deal with these, is both not great at supporting technical or domain changes as a result. And this naturally leads on us to thinking about how do we create more cohesion? How do we decouple our systems a bit more commonly? The next pattern that we typically have is the sort of layered architectures, right? So the MVCs of the world. So here we have a presentation, a service, a business, service, persistence, and database layer. And so this is a really good example where we might think about, okay, what happens if we want to swap out our database? What happens if we want to replace Oracle with MySQL? Okay, we know exactly which layer in our sort of code base we have to make the change for. So technical change, yes, we're pretty good there. But what happens if we actually need to make sort of a business change? What happens if we add a new sort of feature to, or a new attribute to a domain sort of object of some sort? Well, we actually have to start to think about how do we make changes to every layer. And even though there may not be any business change, we might need to still make a change in the business layer to keep things consistent. And here is where there's an interesting trade-off of we add more complexity, more code to the code base, just to add an extra field of copying information that was entered from a user onto a domain object, onto a persistence object that might then be persisted. Now, you might choose to skip a layer and say that's OK as well, because you don't need to make that extra change. But then also you introduce inconsistency. And these are some of the difficult choices you have to make when you think about architecture. What model do you encourage? What would make change easier over time? Now, some frameworks that encourage this behavior obviously are sort of Spring MVCs, Spring Boots, and also Ruby on Rails. Now, the microkernel architecture is very interesting. So in a microkernel, you have a core system, and it's designed around plugins. A really good example of this are Maven, Eclipse, and Firefox. Now, what's interesting about the microkernel architecture is that you have a whole bunch of things already provided to you from this kind of kernel. And then you can extend it through different sort of plugins. And so as long as the plugin interface allows you to extend functionality, you can add new domain changes, and possibly can make changes technically as well. So you can use different programming languages, perhaps, to plug in, depending on the interface. One of the disadvantages with the microkernel architecture is that you don't have any choice to change the microkernel. And so this is where you have to make a big bet on whether or not that matches to the domain that you're actually building for. So as an example, if you choose to build your application on top of Firefox's application, it'll be really hard to make it not look like a web browser. You'll notice this with tools that are built on Eclipse. You'll notice, oh yeah, well, you know that's Eclipse framework underneath the hood. And that's because you can't make any changes to that microkernel architecture. And so there's a trade-off point there. And this is probably where microservices is probably most relevant and why it's become more popular today. And I will say that this is intended to be a well-designed microservices architecture, so there's a couple of characteristics. Services that are bounded around domain entities where there's whole ownership, and there's low coupling across it. You can still do distributed monoliths, which I wouldn't recommend, but the idea here is that you've got a well-modularized microservices ecosystem. Now, what's interesting in a microservices ecosystem is that you can upgrade elements of it depending on your needs. So perhaps we need to change our customer module, and we want to understand what is the relationship of our customers in a graph of some way. Well, we can actually swap out a relational database for a graph database, and no other services need to be updated at the same time. And so we've actually isolated a change that's both domain and technically possible in a particular microservice. Now, there are interesting trade-offs here as well, because we've localized the change, but then we have inconsistency across the entire set of services. And this is an okay trade-off if your organization allows this. So microservices is often requiring quite a lot of maturity to both run and operate this, but also you generally need more engineers in order to keep up to date with this. So if you have the rule of services owned by a couple of teams, and they can evolve those services, their change becomes easier, and it doesn't matter if it's not so consistent across the wider ecosystem in your organization. But this is one of the reasons why this is probably becoming a lot easier and more popular today, is that it supports both our technical changes and domain changes over time, because we can do this in an incremental fashion. We can easily roll things back without affecting everyone else if it turns out to be the wrong choice as well. So we've looked at the three elements of what we describe as building evolutionary architectures, and I want to touch upon a couple of the interesting practices and sort of anti-patterns before sort of closing off. So one of the practices that really go well with evolutionary architecture is this idea about Conway's law and this relationship between the org design and the architecture. Now, if you've been listening to the sort of microservices world, you'll have heard about Conway's law quite a lot. And it's the idea of the communication pathways get reflected in the system architecture of choice. So if you build your organizations in separate functional groups, you'll tend to have much more decoupling across those groups, and that reflects in their architecture. So in this example, you have a user interface team, a server-side team, and a DBA team. And you'll naturally have more resilience because people on those teams will work closer together, and they'll have to have stricter interfaces with other people, and so you'll get natural decoupling across that. But if that's not the change that you want to optimize for, and you want to actually optimize for fast changes in your sort of domain, you actually want to start thinking about changing your team and organizational structure to reflect the ownership from end to end, so you get fast incremental change. And so this is what we call the inverse Conway maneuver. So if you're thinking about the software architecture you want, you have to go beyond the systems and the applications. You have to actually start thinking about how do you design your product team structures, and how do they work well or not well with each other. Another thing that really helps in your sort of organizations is really starting to think about principles over rules. So the automated fitness function that I talked about before was a little bit more like a rule. We don't want cyclic dependencies, right? And the thing with engineers, and you have smart, intelligent people, is that they'll find ways to work around it. And so the thing that you need to do is actually empower people to understand what are the things you're optimizing for, and what are the principles of the things that you care about in your sort of overall ecosystem. And so I'd encourage you to start thinking about what are the top 10 principles of how people should make decisions. Engineers are making decisions all the time as they choose a library, as they decide to put code in one place or the other. And so you need to help people make better decisions as a result. And having good principles can actually help with that as well. Another element that we've found hasn't really helped with building evolutionary architectures is this idea of product versus project-based thinking. Now, in the sort of 90s, where change was coming in sort of every 6 or 12 months sort of cycles, you'd initiate projects. And this is kind of the way that a lot of people would run sort of their organizations. So we'd commission a project, we'd get a team together to make out what changes would need to happen, we'd get those people to work on that, and then we'd sort of disband those people, and then a new project would actually begin. Now, any of you who've worked in these kind of organizations will start to realize that makes change really hard over the long term, because the people who had knowledge about how a system worked are now distributed somewhere else. You have a whole bunch of new people coming in trying to understand what the existing domain rules are, what impact is there, why did they leave behind this legacy of strange decisions? And there were probably good reasons for that. They're just not there to tell you. And so this is one of the ideas behind moving away from this idea of project-based thinking, and really favoring a longer-term team around a domain and the services that they own. And this is really popularized by Amazon's two-pizza team. So you build it, you run it, you own it, and you also live with the consequences. And so this is one of the interesting things with building evolutionary architectures, is you're giving feedback to the people who built that system as well, so they make better decisions over the long term rather than for the short-term project deliverable. Now, one of the other practices you can think about is this idea about keeping decisions to the last responsible moment. So hopefully in a lot of your sort of software, you start to think about your internal code and what are external dependencies on libraries, tools, or platforms that you rely on. And in a lot of organizations, you might start to think about there's multiple places that you might actually be interfacing with some sort of external provider. And you don't want them to directly call those APIs, because if you think about the change, that will take a lot of time to make those changes in multiple places over time. This naturally leads us to evolving an adapter, which is basically thinking about what is the centralized interface in your code that represents this domain concept. And then that adapter component is really responsible for interacting with that externality. Applied at a broader scale to your architecture, you end up with what is called the ports and adapters architecture that was coined by Alistair Cockburn, or hexagonal. The idea being the core of your domain is the things that you want to keep and own, and you use adapters to sort of keep the externalities out, so that if you have to swap those externalities, you only have one small part of your code base to really think about to swap that out. And so this is a really powerful practice that can help you evolve your system over time as well. But I will say this isn't necessarily the excuse to abstract all the things. So once again, this isn't really about trying to anticipate all the changes that you might need to have, but really trying to be pragmatic about if you do it a couple of times, think about the next change, about how hard would that be, and then constantly refactor, redesign, and re-engineer to make it easier for the next time as well. Now, I don't have time to talk about the role of an architect in today's world, but one thing I will tell you is really thinking about the mindset, is that back in the days, the architect was thought as the person who makes all the important, difficult to make decisions. And in today's world, everyone's making changes all over the time. You can't stop them. Engineers have to make decisions. And the behaviors of a good architect today is really a lot more like thinking like a town planner. So a town planner isn't really going to every single house and then saying, no, you can't do that, no, you can't do that. They're really starting to think about the infrastructure and the zones that allow people to operate more independently within their area. They start to think about what makes sense from a connection and infrastructure perspective to allow people to work together. And so really this is really starting to help you think about if a lot of architecture is about making decisions, help people make better decisions. So train people on the ideas of fitness functions. Train people, get more knowledge about what you're actually optimizing for, and equip them with the knowledge to make better decisions. So avoid making the decisions for them. So we've covered a lot of different sort of practices that are both technical and domain that help you build more evolutionary systems. I want to close with a couple of quick anti-patterns that I'd encourage you to avoid. One of them is what we call the last 10% trap. So you'll have these tools that promise to get you lots of productivity really rapidly. And then you'll find you hit some sort of limit. So you might need to configure something, and you have to do some funny workarounds to make that extra change actually possible. This is what happened with the 4GLs of our world. They get you really rapidly to somewhere, and then they stop because they can't cope. And then in that last 10% change, you just can't find the extra workarounds to get what the business really wants. And so this is where you have to really be careful about tools that promise you rapid productivity, that will solve and replace all software engineers. And this is what we call the last 10% trap. The other trap that we want to talk about is really about product customization. So this is particularly appropriate in today's world of SaaS-based software, is it may be tempting to ask a vendor to make some special rules and changes for your business. But one of the things that you need to think about is how long will that product be around, and how will that evolve from the direction where that product is going. And what we've found over time working with a lot of different customers is really that actually it's better to change your process to match your tool rather than customize a product, because the cost to customizing and supporting that over the long term will be a lot harder. And one of the reasons for this is that we're not always thinking about where it makes sense to choose evolutionary architecture versus build or buy. So I want to close by giving you some advice. When we're making decisions, we often think about this sort of dilemma between build or buy, but it's not really a binary, it's a bit more like a spectrum. And one of the things that we tend to view tools through is really this idea of what does it get us? What functionality does it give us? So if we have to write code, wow, we have to write a lot of code to get all the things that we want. But we can just go for products, because it does almost all the things that we want. We just need some customization. And libraries and frameworks are kind of in the middle here. What I challenge you to do is really start thinking about through the lens of how easy it is to change over time as well. So with custom code, if you have good engineering practices, you should be able to make much quicker changes to the systems that you have. If you're trying to work with a vendor to get the changes that you want, it may take 6, 8, 12 months to get them to put it on the roadmap, to agree the contracts to actually get that done. You may not ever get there. And by then, your business may have changed, and you may not need that anyway. So think about change through different eyes, and here's a magic quadrant for you to sort of leave off with. When I think about systems, you can think about them, are they in terms of value generating, and do they need to change over time? You can think about commodity systems, like email systems. You probably don't need to build your own email system unless you're Google or Microsoft. At the same time, there are some systems which I call support systems. They're not value generating, but you may need to make some sort of configuration tweaks for a workflow. So think about these as your Zendesks or your ticketing kind of systems. And then you have things that are experimental, the things that are potentially high value generating, but if they fail, they may not actually need change. You throw them away, you discard them. And what I posit is that you have this sweet spot where evolutionary architecture makes sense. These are the strategic systems. These are the things that are at the heart of the businesses that you run, the things that make your business different. And this is where you really want to be investing in these techniques that I've talked about with building evolutionary architectures. So hopefully you've understood that what we talk about in terms of evolutionary architecture are systems that support incremental guided change as a first principle among multiple dimensions. And I ask that you consider it's more than just architectural choices. It's also about the decision-making process in the environment that you create, and also organizational and cultural aspects that make change easier or harder in your organizations. Thank you.